Well, good evening in Tokyo, good afternoon in Paris, and good morning from the United States. And welcome to this concurrent session of the 7th annual meeting of the Innovation for Cool Earth Forum, ICEF2020. I'd like to thank the organizers for making this session possible, and I'd like to welcome the panelists as well as others who are on the call. I'm going to introduce the panelists very shortly. Our topic is innovations in nuclear energy and how these will help address the challenges of the future. Probably the greatest challenge the world faces is to manage the threat of climate change. And our panelists are going to discuss different aspects of the nuclear role in meeting this challenge. But I'd like to kick off the session with a few more general comments about why innovation matters for climate change. Perhaps I could have the first slide, please. Let me suggest 3 reasons why innovation matters for addressing the challenge and the threat of climate change. First slide, please. The first point I'd like to make is that some people say that what is more important than technological innovation is behavioral change. That the only way we can hope to cut back on greenhouse gas emissions effectively is to consume less, to travel less, and to use less energy generally. Unfortunately, this won't be enough. Next slide, please. We've just conducted one of the biggest experiments in behavioral change in human history. And even at peak lockdown in April of this year, the world only experienced an estimated 17% reduction in carbon dioxide emissions. And we will likely see no more than an 8% reduction, probably not even 8% on the year, despite the enormous disruptions and lost economic output around the world as a result of the pandemic. So yes, we'll need behavioral change, and we'll need the education and the public policies to promote it, but we won't get to net zero emissions that way. A second point. Next slide, please. Some people say, yes, technology is important, but actually we have all of the technology that we need, and that what's really lacking are the right policies and the political will in our various societies to enact those policies. And for some people, the most important such policy would be a robust policy for pricing the carbon emission externality or the greenhouse gas emission externality. But while it's certainly true that there is much that we can and must do with existing technologies, in fact, we don't have all of the science and technology that we need. There are many hard problems that still need to be solved, that are unsolved, for which economically viable solutions, or in some cases, solutions of any kind, do not now exist. Next slide, please. And please build the slide. There are 2 or 3 builds, and just to save time, could you go through the next 2 or 3 slides? Thank you. For example, solving the central problem in low-carbon electric power systems of achieving a real-time balance between supply, which of course fluctuates because of the intermittency of solar and wind and this will become more important as they take on more of a role in our electric power systems, a balance between real-time supply and demand, which of course fluctuates because we don't consume electricity at a constant rate throughout the day or throughout the year. And how will we achieve this balance without natural gas or other fossil fuels to keep things in balance. Getting to zero will also mean tackling the 60% of global carbon emissions that are not produced in electric power generation. And here there are tougher nuts to crack. In the industrial sector, cement and steel production, which today account for about 10% of global emissions. And today we don't know how to make these without emitting carbon. And long-distance freight transportation by land and by sea, and also aviation. Taken together, these activities produce as much CO2 as automobiles. So yes, we have existing technologies that we need and must use, but there are new problems that must be solved with new science and new technology. A third argument against innovation, next slide please, is that there isn't enough time for it. We need solutions right away. And it is true that we're facing an emergency and that there is indeed no time to waste. We must do what we can immediately, and it is also true that innovation can't happen overnight. In fact, it takes many decades to transform huge global systems, transportation, electricity, industry, buildings, and so on. But if we tried to do this with existing technologies, it would be extremely expensive. And so, as we consider in this session the role of nuclear energy in addressing these challenges, I hope we'll be able to consider all of these issues and all of these questions. And now let me very briefly introduce our very distinguished panel. We have four leaders in the United States, we have four leaders in the nuclear field from Japan, from the United States, and from the Nuclear Energy Agency in Paris. And our first speaker will indeed be Dr. Bill Magwood, Director General of the Nuclear Energy Agency. Next, we'll have Dr. Jill Engel-Cox, the Director of the Joint Institute for Strategic Energy Analysis at the National Renewable Energy Laboratory in the United States. Our third speaker will be Dr. Ashley Finan, Director of the National Reactor Innovation Center at the Idaho National Laboratory. And our final speaker will be Nakatani Eri, Acting Director for Nuclear Technology in the Nuclear Energy Policy Planning Division of the Agency for Natural Resources and Energy of the Ministry of Economy, Trade and Industry of Japan. We'll go through each of these four presentations, and then we will look forward to a period of discussion among the panelists and hopefully questions from the audience. Thank you, and let me now hand over to Dr. Magwood. Bill?
Good morning. I'm Bill Magwood. I'm Director General of the Nuclear Energy Agency. It's a pleasure to speak with you today about nuclear energy innovation. Let me begin by talking about the NEA itself. NEA is an association of governments. We have 33 members. They represent the deepest experience in nuclear safety, technology, and policy around the world. We operate through a framework that brings our member country experts together through committees and working parties in which they work on very specific issues of technology and policy. We also conduct 23 international joint projects in areas of nuclear safety, radiation protection, and nuclear waste. The NEA is also the home for the Generation 4 International Forum, the Multinational Design Evaluation Program, and the International Framework for Nuclear Energy Cooperation. Our work in recent years has been impacted by the world agreement reached in Paris to limit increases in global average temperatures to well below 2 degrees C. This translates into a very stringent 50 gram of CO2 per kilowatt hour target for electricity production. This is very aggressive, and it will require that within the OECD countries, that emissions reduce by 85%. Very, very difficult. Countries hope to do this using variable renewable energy. There's been a great investment in VREs around the world, and we think there's a lot of benefits to this. However, the facts show that emissions have continued to increase. Before the pandemic, we had a new peak in CO2 emissions around the world. If we're going to be successful, we have to find the right approach to long-term economic and reliable electricity supply. Our work in this area shows that we will need all low-carbon technologies if we're going to be successful, but they have to be applied in an optimal way with all the costs accurately allocated. In order to do this, electricity markets must be modernized in order to provide the right price signals and the right incentives, and also provide the investment resources necessary to pay for these new technologies. That is not happening today. While we at the NEA can perform analysis like this for member countries, it's really the markets that need to change to provide these cost signals. However it ultimately is decided, we believe that there will be an optimal mix between dispatchable resources and variable resources. To the degree that dispatchable resources are necessary, nuclear has a very large window of opportunity to expand around the world, if it's economically viable. Many people use LCOE to consider nuclear versus other sources, but we find that's not how countries are making decisions. More often, countries are looking at the sticker price, the cost of building a new nuclear power plant. As you can see in this chart, based on a generic case, nuclear is significantly more expensive than other options when it comes to the initial capital cost. In reality, the projects we've seen in Western countries around the world, in France, in the US, and in Finland, these costs are actually twice as high. That's not sustainable, and we have to do better. The good news is that now that we've been through initial projects in various countries, we think that we've now built supply chains and built experience that would make the next plants much less expensive. We just issued a report on that basis. However, what we also see is that countries are moving in a different direction in many cases. Many countries are focusing their attention on small modular reactors. This is, of course, a very exciting development. These new technologies promise high flexibility, manufacturability in factory, and have safety characteristics which really can be truly game-changing. Imagine that a nuclear power plant that does not require off-site emergency preparedness. There are many types of designs that are being developed. By last count, there's somewhere around 60 different designs around the world that are being developed, mostly by private companies, to meet these new targets. Many of the technologies are what we call these single-unit LWRs. These are based on LWR technology, but are much smaller. They can be deployed in a manner where they can be fitted to come closer to the demand centers. There are also the multi-modular LWRs, which in some cases can look a lot like a baseload power plant functionally, but be much more flexible and much safer. There's also interest in mobile SMRs. We think that this is an interesting area of technology, but there's many questions about the regulatory and legal approach that will be taken to oversee their operation. And many countries are also interested in what we call micro-modular reactors. These are very small units that will be placed near the mines or small communities that require power. This is of extreme interest in, for example, in Canada that has many remote communities where it's very difficult to move fuel oil. We'll see how this transpires because there's still many questions to be resolved. In the longer term, and of course there are some that think this will not be that long, but Generation 4 SMRs are also of great interest. These could completely change the conversation about nuclear power by providing not just the typical electricity generation, but also the ability to recycle materials and to provide heat for industrial and residential purposes. There's a wide range of these technologies. They're very interesting, and we'll look forward to seeing which ones make it to market soon. But whatever technology is selected, there's going to be a tremendous challenge to do this globally. Nuclear has often been a domestic industry, but if for the SMRs to be successful, we're going to have to see a change. We're also going to have to recognize that if we can share some of these costs, it would be an advantage to everyone. But if these technologies are going to be successful, they're going to have access to the world market, much like the aircraft industry. Aircraft manufacturers do not build an aircraft for one country. They build it for a global market. I think SMRs are going to have a similar type of outlook. Otherwise, it will be very difficult to recover the costs necessary to set up the manufacturing runs. At the end of the day, the hardest part of this will probably be the regulators. Can regulators come together to have a global approach to licensing SMRs? If SMRs have different licensing requirements in every country, it's going to become a major barrier to progress. I'll close with making the observation that there are many NGOs and other experts that think we simply use too much energy, and that we should perhaps start riding bicycles instead of driving cars. And of course, there's been a suggestion that maybe taking a sailboat across the ocean is better than flying in an airplane. And there's even been those who have suggested that countries that are trying to pull people out of poverty and improve healthcare, improve the lot of future generations, maybe should have to delay their plans a bit in order to save the environment. This is not going to work. The public in all countries will not accept giving up civilization in order to save the environment. If we're going to be successful in saving the climate, we're going to have options that provide access to economic growth and freedom without damaging the environment. We have to have it both ways. We have to be able to have reliable electricity across the world at the same time we reduce CO2 emissions. We believe that nuclear energy provides a pathway to do this. And we believe that nuclear in combination with renewables and other options would make it possible to see the Paris Agreement implemented successfully. But if that's going to happen, we have to start now. With that, I will conclude my remarks and thank you very much for your attention.
Hello, my name is Jill Engel-Cox. I'm the director of the Joint Institute for Strategic Energy Analysis at the National Renewable Energy Laboratory in Golden, Colorado, United States. I'm going to talk about flexible nuclear energy for clean energy systems, which is part of work that we've done for the Clean Energy Ministerial as part of an initiative called Nuclear Innovation, Clean Energy Future, or NICE Future. So as a renewable energy research institution, we study the different types of renewable energy technologies, including the leading variable renewable energies of wind power and photovoltaics. And a number of years ago, we became interested in how renewable energy interfaces with traditional energy sources. And this is particularly important because as variable renewable energy becomes an increasing part of our energy system, that there will be times that you will want to use the low-cost, low-emissions renewable energy from wind and solar, but you'll also have thermal systems, such as nuclear power, that you would want to operate continuously because they are a very large capital investment and you will want to use them and not cycle them down or shut them down while you have a lot of renewable energy on the system. So you have this dual challenge of some types of renewables being variable and some types of traditional energy, particularly nuclear reactors, being inflexible or not able to adapt to the different types of energy demands. So we begin to do some systems modeling and systems analysis to consider these collectively and how you can combine low emission sources such as nuclear and renewables to provide electricity to the grid. And then when you have excess electricity because of high renewable resources and you're wanting to operate your nuclear reactor at full capacity, you can use those excess electrons to create hydrogen through an electrolyzer, which can be used to store to be then later generate electricity later through a fuel cell, or can be sent to the industrial and transportation markets. We also included in this systems analysis the consideration of thermal energy, which there's a large amount of thermal demand, and how you can use the thermal energy from a reactor directly at the times when you do not need it to produce electricity. So what we learned by evaluating this systems approach is that you can actually complement various types of clean energy systems together into an overall system, especially if you consider power, heat, and various types of chemical and fuel storage. This ultimately led to us getting involved with a new initiative on the Clean Energy Ministerial. We actually operate several initiatives for the Clean Energy Ministerial. And several years ago, it was proposed to launch a new initiative, the Nuclear Innovation Clean Energy Nice Future Initiative, which explores the potential for nuclear energy uses, innovations, and systems integration to accelerate the progress towards clean energy goals. And the initiative recognizes that there's no one-size-fits-all solution to energy. So each country will have its own different approach. So the way France operates its reactors would be quite different from the way the United States may do that, as well as new nuclear countries such as Jordan. And this, you can see the lead countries there and participant countries gathered together with the goal to pool together the experience of those countries related to economics, related to policy, and related to innovative applications of technology to both electricity and to non-electricity. There's also a large number of external partners involved with this initiative as well, and you can see a website there for more information. One of the things that we did this most recently was begin to explore this concept of flexibility. And so this past year, we compiled chapters from multiple authors from multiple countries, 9 different energy ministries, 5 multi-government organizations, and 14 other organizations, and you can see the flags of many of the countries there, who provided technical content and experience about how they can see nuclear power operating flexibly, either currently or in the future. The goal being to share information between multiple countries, to learn how each has operated their system in a way to maximize emissions reduction. This slide just really shows the contributions from the many different types of authors and organizations that were involved in the preparation of this report. Our key findings from the Flexible Nuclear Energy Program, well, first we had to define flexibility. And you can see the definition there, which in terms of nuclear flexibility, it's the ability of nuclear energy generation to economically provide energy services at the time and location they are needed by end users. And we also included that this would be both electric and non-electric applications using both traditional and advanced nuclear power plants. And we determined that there was 3 key types of flexibility. There was operational flexibility, and there's a lot of established body of knowledge about how you can operate reactors in different ways to make them more flexible. There's product flexibility. So this is looking at using existing reactors to produce both electricity as well as beneficial non-electric products. This could be heat, this could be hydrogen, this could be other types of services that they may provide to the energy system. And then finally, the final tool is deployment flexibility. And this is, as we begin to get small modular reactors and different size reactors, they'll present even more opportunities for flexibility in the system. So you'll be able to combine them to provide larger amounts of power, or you may be able to deploy a single small modular reactor at an industrial system to go forward. So really, flexibility can be achieved through these multiple different ways: operational, product, and deployment. And the report has these written up in detail of how people have experienced going forward. And really, the part of the flexibility is really imagining how nuclear and renewable systems can work together. It can be looking at remote communities. It can be looking at industrial processes. It can be looking at desalination, or it could be looking at campus power. And really the goal is to be thinking about new applications at different scales and providing multiple different services to different types of organization going forward. And the ultimate goal is to be able to combine these and enable other types of clean energy systems, such as renewables, to create an overall energy future that has lower emissions. So thank you very much, and I look forward to answering any questions.
Hello. Thank you for the opportunity to present at the Innovation for Cool Earth Forum in the Innovations in Nuclear Energy session. My name is Ashley Finan, and I'm the director of the National Reactor Innovation Center based at the Idaho National Laboratory in the United States. You've heard from other panelists about the importance of nuclear energy innovation to address climate change. Our approach to nuclear energy demonstration, I believe, can help us demonstrate advanced nuclear technologies and prepare them for commercial use in a time frame that is consistent with addressing climate change. In these slides, I will share some of the highlights of our approach, but I'd welcome outreach afterwards if you have further questions. First, we are committed to demonstrating advanced nuclear reactors by the end of 2025, and we're working to do that through our mission to inspire stakeholders and the public, to empower innovators to test and demonstrate their technologies, and to deliver successful outcomes through efficient coordination of partners and resources. Our big picture 5-year program objectives are enabling the demonstration of at least 2 advanced reactors by making available infrastructure and other support, and to prepare the U.S. Department of Energy and national laboratories for continuing innovation and demonstration by developing best practices in demonstration and also developing enduring infrastructure and expertise and methods for coordination among the laboratories. Some are discouraged about the pace of nuclear innovation and are not sure that we can do this. But history counsels us to be more hopeful. In fact, we haven't done this recently, but we have done this before. At the National Reactor Testing Station at Idaho National Laboratory, the United States built 52 different reactors over about 25 years. At Oak Ridge National Laboratory, the X-10 reactor was built and commissioned in under 1 year. We have a successful history of rapid demonstration and innovation when faced with an urgent need. And we're going to do it again. But we've learned, and we're going to do it a bit differently this time, with some refinements. So I'm going to walk through some of those refinements and explain why I think they are important. The first modification is that we are intensely focused on empowering innovators in the private sector. Instead of being government-directed, this is a private sector-driven effort with access to government resources. The National Reactor Innovation Center is preparing a resource team to assist innovators with planning. The U.S. government is providing funding to help innovators build their demonstration projects. And NREC is developing a demonstration resource network that includes experimental facilities, fuel facilities, test beds, which I'll explain in a moment, and demonstration sites for advanced reactor demonstrations to be built. The images here on the top right shows a test bed facility design. The bottom right shows a modular hot cell for some thermophysical examination capabilities, and then the bottom left shows some modeling and simulation capabilities that we're developing. We have a vision of this demonstration resource network as being a national network that encompasses the various key competencies around the country to support demonstration. This slide shows what a demonstration test bed is. So the diagram shows the blue systems that are the testbed systems and the green systems which belong to the demonstration reactor and are temporary. Our role is to refurbish existing facilities to enable them to host private sector demonstrations. The photos show two different facilities. The top right is the EBR-2 dome, which previously hosted a demonstration reactor. And then the left on the top is the zipper cell, which hosted zero power physics reactor experiments and is suitable for a smaller demonstration. So we've completed pre-conceptual design on these, and in 2021 we'll complete preliminary design and begin final design. This will enable long-term innovation and continuing innovation as we move forward in time, not just a one-time demonstration. Next, the next modification, number 2, is addressing cost and markets. This wasn't a strong element of the first wave of nuclear demonstrations, but we are emphasizing it. We're using digital engineering, which has been proved to improve cost, schedule, and quality. We're working to demonstrate advanced construction technologies that could reduce the costs and schedule overruns associated with civil construction of nuclear power plants. And we're working to demonstrate integrated energy systems alongside other DOE programs in order to show how nuclear can integrate with the smart grid of the future. The next station that we see as vital to our success is proactive impact management. We're addressing our environmental impacts. We are here to make things better, to address climate change. We need to ensure that we also make them better in the local area and the demonstration sites. So we're working to do environmental impact assessments by doing cultural and biological surveys of sites, by developing a plant parameter envelope that we can use to evaluate both environmental impacts and safety impacts without having the specific detailed design of the reactor ready. Instead, we're enveloping that design, taking into consideration all of the designs that we think might be demonstrated. And we're looking at water use. Idaho National Lab is located in the desert, so that's particularly important there. Also, we're looking carefully at the back end of the fuel cycle, at packaging, storage, transport, and disposition. And finally, modification number 4 is engagement. We need to make sure that we are engaged with the communities that will support this, that will benefit from this, and that may have concerns about this. We're working with partners to develop best practices in engagement, and this slide shows a few of the tools that we're developing to communicate with our stakeholders. On the bottom left is the NRIC website. On the bottom right is a flyover visualization of some of the sites and capabilities at Idaho National Laboratory. On the far right is a mapping tool we're developing for the Demonstration Resource Network. And then on the top are some visualizations of specific sites that allow you to zoom in and take a look at the land that we have identified for advanced reactor demonstrations. So in summary, the National Reactor Innovation Center demonstration approach that we believe can move faster and more effectively than the older approach is to empower innovators by providing key infrastructure, expertise, and capabilities, while the U.S. Department of Energy provides a cost share for industry demonstrations, to address key cost and market challenges that are important to deployment, to take a proactive approach to local impacts on the environment and the community, and to have a robust engagement strategy that involves the communities in a positive way. Thank you very much for the opportunity to speak with you today. I hope that this has been helpful, and I look forward to the discussion.
Ladies and gentlemen, distinguished guests, it is a great honor for me to give a speech at the Innovation for Cool Earth Forum. I am Eri Nakatani, Acting Director for Nuclear Technology at the Agency for Natural Resources and Energy, Ministry of Economy, Trade and Industry of Japan, in short, METI. I joined METI in the year of 2011, straight after the accident at the Fukushima Daiichi. It has been almost a decade since the accident, but we shall not forget what has happened and what could possibly happen in the future. That is the reason why we put safety first when it comes to restarting the existing nuclear fleet. As mentioned in the 5th Strategic Energy Plan, last updated in 2018, only when approved by nuclear regulation authorities, strict safety reviews, nuclear power plants will restart. Looking to 2030, we still regard the existing nuclear fleet as an important baseload power source. However, we also recognize that nuclear power may just be one option for energy decarbonization in 2050. But two things are clear. For nuclear power to make a meaningful contribution in 2050, we need to keep strengthening human resources, technologies, and the industrial base. In addition, we need to pursue safe, economically efficient, and flexible reactor systems and development of back-end technologies by encouraging competition among various nuclear technologies. Here, I listed 6 potential needs for nuclear innovation in this decade or decades to come. First of all, safety. The Fukushima accident tells us that we have to be prepared for any thinkable or even unthinkable events, including natural disasters. Many advanced reactor concepts talk about passive inherent safety features. Radioactive waste management is another area to be focused on, as some reactor concepts, such as fast reactor, can drastically reduce the time of radiotoxicity. Non-proliferation also needs to be cared about, as emerging countries think of importing these new types of reactors. Flexibility, mobility, and multipurpose use are also important when lots of intermittent renewables are introduced into the grid. Nuclear could be more flexible, mobile, and could be used for hydrogen production, heat utilization, and even energy storage. Besides complementing renewables intermittency, nuclear could be an important carbon-neutral source when the sun does not shine and winds do not blow. Economic efficiency is also important, as renewables may become zero marginal cost, as well as carbon-neutral energy sources. Cost reduction innovation on the capital cost of nuclear is necessary. For that to happen, continuous improvement of existing technologies, as well as the solid industrial base to support that, would be important. In order to address these needs, Japan started the NEXIP program, Nuclear Energy Innovation Promotion Program. This is an initiative initiated in 2019 to help accelerate the development of innovative technologies in the private sector through cost-shared funding support, access to R&D facilities, and human resource development efforts. This is a joint effort supported by METI, the Ministry of Science and Technology, MEXT, and the Japan Atomic Energy Agency, Japan's national lab. Through the funding support, we support private companies' feasibility studies of state-of-the-art reactor concepts, as well as associated technologies such as technologies to enhance safety and digitization, as well as new types of fuel. As for the R&D facilities and resources, JAEA National Lab can provide its state-of-the-art research facilities and share its knowledge with private companies. We also would like to enhance collaboration between the private sector and academia, as well as with the international communities. Besides many human resources development programs we support, we also recognize this initiative as an important means for private companies to stay active and innovative. If the nuclear sector wants to attract talents, we need to keep innovating to address societal needs. Through this NEXT program, METI supports feasibility studies of various advanced reactor technologies, including small modular light water reactor, fast reactor, and high-temperature gas-cooled reactor. SMR, because of its smaller size and module production, has a smaller source term and a reduced construction period, which may lead to affordable capital cost and enhanced safety. The United States, as well as UK, Canada, and other countries are the most active in this field. And we are exploring new ideas for SMR, as well as opportunities for international cooperation in NEXT. Sodium-cooled fast reactor utilizes fast neutrons, which enables effective use of resources and reduction in radiotoxicity of high-level waste. Japan is promoting fast reactor R&D based on its strategic roadmap. In this decade, we will try out many fast reactor concepts, which will eventually lead to realization of the first commercial fast reactor around the middle of the century. We also regard international cooperation as important in the fast reactor R&D, and we cooperate with France based on a renewed arrangement started this year, as well as with the United States on its versatile test reactor, VTR, based on the MOC signed last year. We believe JOYO, JAEA's experimental fast reactor, is expected to make an important contribution to fast reactor R&D, domestically and internationally. Japan also prizes its high-temperature helium gas-cooled reactor technology. Helium is chemically stable, unlike water. Helium gas and coated particle fuel allow the reactor temperature to rise to as much as 950 degrees Celsius, recorded in JAEA's test reactor, HTTR. This very high temperature can be utilized for heat utilization as well as for hydrogen use. And this is very safe. The last two slides are a little bit technical, but I would like to go a little further to explain about JAEA's facilities. Experimental fast reactor JOYO, which reached its first criticality in 1977, is expected to return to the operation soon after its safety review based on new safety standards passes. JOYO enables irradiation tests under controlled temperature, which could be increased to as much as around 800 degrees Celsius, and provides the highest level of neutron flux. Various test materials can be irradiated simultaneously in the irradiation assemblies under very finely tuned, high-energy neutron spectrums. Experimental HTGR, called HTTR, reached its first criticality in 1998. Since then, it has been making history. In 2004, the reactor outlet coolant temperature reached 950 degrees Celsius, the world's highest record, and achieved 50 days of continuous operation in 2010. Together with OECD countries, JAEA conducted loss of force cooling test, which proved that the reactor can be naturally shut down as soon as the core cooling flow rate is reduced to zero. It has already passed the NRA's most stringent safety review and is expected to restart after next year. To conclude my presentation, advanced reactors have the potential to address future needs besides decarbonization, such as enhanced safety, flexibility, radioactive waste management, etc. Japan, among other countries, encourages competition among various advanced nuclear technologies through its cost-shared support program. Lastly, international cooperation is the key to success. Thank you very much for your attention.
Well, I'd like to begin by thanking all of the panelists for their really excellent presentations. Clear, to the point, just outstanding. I want to apologize to the audience, if not the panelists, for not introducing myself previously. We skipped over the introductory slide, and in case there was anyone who didn't see it go by, I actually didn't see it go by. Let me say that my name is Richard Lester. I am Associate Provost at the Massachusetts Institute of Technology, where I'm also the Japan Steel Industry Professor and Professor of Nuclear Science and Engineering. Again, I'd like to thank all of the panelists for their really excellent presentations. And if I may, I'd like to begin the discussion with just an observation and then a question. And I think the question is for all of the panelists. The observation is really just to highlight a point that Bill Magwood made in his talk. He said, we have to have it both ways in our energy systems. We have to have reliable, affordable energy that is also low carbon energy. And of course, that frames our discussion today about the role of nuclear energy in these energy systems. But my question to start the discussion is really about priorities. What we've heard from the panel is that different kinds of innovation are necessary in the nuclear field. And the question is, what are the most important priorities here? We have seen a reference made, especially in Jill's talk, but in others too, to the importance of flexibility. And she made a very useful set of distinctions between operational flexibility, product flexibility, and deployment flexibility. But of course, we also heard about the importance of safety. And we heard about the importance of environmental impacts, including waste management. And we heard about the importance of cost reduction and related to that, importantly, responsiveness to changing markets. And finally, although I don't think anyone actually mentioned it explicitly, let's not forget the importance of contributing to non-proliferation goals. So all of these objectives have been identified. All of them are important. But to start the discussion, I'd like to ask our panel, how would you prioritize among these different objectives? And perhaps if I can ask Bill to start that discussion off.
Thank you very much, Richard. Well, first, let me also echo, I thought presentations from my fellow panelists were excellent. Of course, I've known Ashley and Jill for some time, so that's to be expected. And Ms. Nakatani, it's the first time I think we've had a chance to meet, and I look forward to having more opportunities to speak with you. Your presentation was very interesting. I'm afraid that the answer I'm going to give you is going to be very unsatisfying, because the answer is going to be that we have to do them all. We really have to prioritize bringing new nuclear into the market in a way where it fits the infrastructure. And the infrastructure has very high expectations. And you mentioned safety, and I think Ms. Nakatani's presentation highlighted safety as well for very good reasons. I look at safety as almost not worth talking about, in the sense that it is so essential to the way the nuclear has to look in the future, that if you're designing, if you're worrying about safety and making your reactor safer, you may have chosen the wrong design. What we need in the future are designs. I put it this way, and sometimes my staff doesn't like this phrase. It's not that we need inherently safe reactors. We need reactors that are already so safe that they become inherently inexpensive to build and operate because of the basic technologies that they use, because of physical laws that keep them from melting down. So we really, as we go forward, we have to have a complete shift in how we think about this. However, I will also add that in the time frame that we have to work with, which isn't that long. I mean, people think 2050 is a long time from now. It isn't. It's just around the corner. So we don't have the time for a long development of brand new technologies. Whatever technologies are going to be effective in 2050, if they're not pretty close to being designed right now, they probably won't be available in 2050. It just isn't enough time. So we really don't have time to develop all new things. So some of the concepts that Ashley talked about in her presentation that are out there, these many different innovations, those have to start to show up very quickly, get to licensing, show that they work, be demonstrated, and be available to the market. And if they're not available to the market by 2030 or so, they're probably not relevant to the timeframes we're talking about. So we don't have a lot of time to fix these problems, but on the long term, I do think we have to have these big innovations. In the short term, I think that the innovations that we need are probably more on the institutional side than they are on the technical side, more about how we structure markets, how we regulate, how we license. I think those are going to be more important in the short term than the major changes in technology.
Thanks very much, Bill. I wonder, may I invite any of the other panelists to comment on this issue of priorities among these different objectives for innovation? Yes, Eri, please.
Very nice meeting you all. Do you hear me now? Okay.
Yes.
Okay, cool. So I really echo Mr. Magwood's comment that safety is very essential, especially for Japan. If we are going to build, if any, a nuclear reactor in Japan or anywhere in the world by Japanese companies, that needs to be safe because we had the Fukushima accident. And for the public acceptance point of view, safety is very essential, especially for Japan. So we would like to, echo that point. And also, as Mr. Magwood said, even if we talk about 2050, we don't have much time. I agree. And in order for nuclear technologies to come online quickly, I think utilizing the established facilities, such as at national labs, is quite important. And that's what also Dr. Finan talked about. Support by the national labs is a key to success for the nuclear technology to happen in any country. So, and also, I would like to say that international cooperation can happen in this field as well, so that the technology can come online quickly. Thank you.
Thank you very much. Let me turn to a somewhat different question, and I think this is mainly for Jill. But a number of the speakers talked about the importance of establishing an optimal mix between dispatchable and variable renewable resources. And I would like to ask Jill, from your studies of integration of nuclear and renewables, are there any further insights that you might want to highlight about what actually constitutes an optimal mix between these sources? Is there a rule of thumb that you could identify that suggests what the relative proportions of these different kinds of generating sources needs to be on electric power systems? And secondly, and related to that, just in the nuclear context specifically, what does operational flexibility actually mean? And what are the highest priorities that you would assign to achieving operational flexibility for advanced nuclear designs?
Well, thank you very much, and thanks for having me on this panel. It's always good to see everyone. And thank you for this excellent question. I think the concept of an optimal mix is very place dependent. I mean, there will not be an optimal mix that is exactly the same for any particular country or location or region. And that's really dependent on a number of different factors. Part of it is the resources within a country or a location itself, and that includes the natural resources. Is there a lot of renewable resources that are available, or there are fewer? What is the demand, the energy demand? What is the way the demand is operating in terms of there's a lot of industrial processes, a lot of urban areas or non-urban areas. So the energy mix is really very place dependent. And then it also, on the resources, it also depends a lot on where a location is from their level of level of industrialization and what their energy demand is, and the capabilities of the people in the industry in the country in terms of where they want to emphasize and what existing capabilities they have. For example, I worked quite a bit in Saudi Arabia, and of course they have tremendous oil and gas resources, tremendous ability to operate those types of systems. And so they're going to have a different type of energy system than, say, Japan, which does not have those levels of resources. And then it also depends a little bit on the societal mix, societal values. What is the society seeking in terms of their goals? Are they looking primarily for greenhouse gas reduction? Are they looking for increased energy, consumption, increased efficiency? So different countries and different regions need to put these together and come up with their options. And then finally, it's really how it may work in a grid system. So how do technologies interact with each other? And that's where a lot of the within those other constraints, how can you model the integration of these different technologies together? And what we've seen in some of our models is that you can have very high levels of variable renewables. 50, 60, 70% we're beginning to see with actually relatively limited storage. But when you get to those very high penetration levels, then it becomes much more difficult. You either have to overbuild a lot of the renewables, or you have to bring on a tremendous amount of storage. And this is where you get integration. If you're looking for a low greenhouse gas emissions mix, this is where nuclear may be able to play an excellent role to be able to operate with those high levels of renewables without requiring some of the higher levels of storage and overbuild. And then that's where it gets into your final part of your question, which is operational flexibility. Obviously, there will be times where you have very low demand, very high production from renewables. And so you need to be able to operate all of your assets, all of the energy assets on a grid system flexibly so that you can provide power as needed. That can be, in France, they're able to ramp their reactors down pretty significantly. And that's one approach. It may also be generating hydrogen, providing heat, providing other energy services so that the reactor appears flexible to the grid because it is doing these other things behind the meter. So that's what we mean by some of the different flexibility. And I think going forward, it's going to be diversity and flexibility is what's going to be really important for our energy system.
Thank you, Jill. And just to follow up on that, and this is perhaps a question for Bill, and then I'm going to circle back to Ashley on a different point. But as Jill said, the requirements and the desirable features of nuclear systems they are to some extent place dependent, and one might say even country dependent. And given these differences in priorities across countries, how can we get the most out of international cooperation in advanced reactor development? This is really a question, I think, centrally for Bill, but others may also want to comment.
That's a very perceptive question. Let me first say that Jill's entire analysis is exactly in line with what we've been seeing as well. I mean, I think it has to be very, not just country specific, but really market specific. You really have to, and one of the frustrations I think that I've had is that I see countries or even agreeing to sort of blanket targets for different capacity of renewable versus something else. And they really should be looking at a market-specific approach to understand exactly what is optimal for their situation, because it's going to be different for different people, for different areas. The answer to your question is it's difficult to answer because we don't know yet. If you listen closely to what Ms. Nakatani was saying and what Ashley was saying, you see the problem. This is no longer government-driven research and development. That is what government-driven research and development is how we formed the Generation 4 International Forum almost 20 years ago. Government operators like NEXT in Japan, DOE in the United States, CEA in France had very similar projects that they were developing. There was room for cooperation to share the cost, to do projects together. It's very straightforward. The modern approach that the countries are taking is to, instead of being the leaders of the technology, to support industry to be the innovators. And as a result, that's why there's 60 or 70 different innovators out there, all competing for money from Japan, UK, Canada, United States, other countries, and all basically in competition, looking to sort through the market. The problem is we don't know how that's going to sort itself out. We don't know what the answers are going to be. And because of that, it's very difficult for countries to have international cooperation because they don't know what the answer is yet. Hopefully, there'll be a sorting process that will become apparent in the next, hopefully, 5 to 10 years. And then you'll be able to say, well, this technology is really of interest in this country, this country, this country, therefore there's room for cooperation. But right now we don't know how to do it because the commonalities aren't there. What countries are more interested right now in developing are cooperations on those institutional issues like licensing, and we've been working on a lot of that. But technology cooperation is very, very difficult in the current environment.
Thanks, Bill. And as you pointed out, there are many different groups, and the other speakers have commented on this too. And of course, in this discussion, we focused only on advanced fission technologies, but there is a almost equally large number of developers, many of them, most of them actually, private developers now, of advanced fusion technologies. And this really raises a question that I think I'd like first to direct to Ashley, which has to do with your observation, Ashley, of the importance of empowering innovators in this next generation of technology development. And I think you might agree, but please let me know if you don't agree, that that there is something here about the importance of fostering an innovation culture in the advanced nuclear field. Empowering the innovators means fostering, I think, means fostering an innovation culture. But the question for you, Ashley, and I think you're particularly well positioned to address this because of your previous position with the Nuclear Innovation Alliance, is how can we balance innovation culture with safety culture in the nuclear field, where safety culture has been central to the work of both regulatory and development organizations across the world in nuclear for so many decades. How do we establish a balance between those two things?
Thank you for the question, Richard. That's an excellent question. I think you're right that we need to have an innovation culture. And part of that, if you're working with private industry to innovate, and it's important to ensure a predictable and a rapid regulatory review, not a less thorough review, but one that is more efficient and also well suited to considering advanced technologies that it hasn't considered before. That's largely the definition of innovation, or it's part of the definition. So if the regulator is unable to evaluate technologies that it has not previously evaluated, that stunts innovation. And if innovators don't understand the cost or the schedule associated with the regulatory process, then they can't explain it to their investors, and their investors lose confidence in their ability to move through the regulatory process. And I think we've seen movement in the United States here really improve upon or modernize the regulatory framework for advanced reactors. And I'm very encouraged by it. I don't see that there's any compromising on standards or compromising on the top-level safety goals. Instead, the regulator has taken an internal look, and of course there have been external efforts to support them with ideas and suggestions, but they've taken a hard look internally at how they can be more agile and how they can be more efficient without reducing the rigor. In fact, what that does is it enables them to consider technologies that are inherently more safe. If you have a regulator who's unable to consider new technologies, that means that they can't consider safer technologies. So improving the regulatory review to make it more agile and less technology specific doesn't need to reduce standards. It can actually drive us towards better safety outcomes alongside innovation. And I think that's an opportunity that the U.S. Nuclear Regulatory Commission is seizing, and perhaps Bill would be able to comment on whether he's seeing that elsewhere, but I would encourage it to take place elsewhere as well.
Thank you, Ashley. And perhaps I could ask Nakatani-san, because I think this must also be an important challenge in Japan, how to balance these two objectives of strengthening the safety culture and strengthening the innovation culture in the Japanese context.
Thank you. I totally agree with Professor Lester as well as Dr. Finan that we need to be agile, but at the same time, we also have to keep the high standard of safety as well. To achieve both, I think we really need to think about what kind of safety we really want to achieve through the innovation. I think lots of engineers are doing a probabilistic risk assessment as well as testing the new technologies in a stringent manner. That's a very important process as well. Of course, innovation means that technologies are not previously existed in the world, so they may fail before they accumulate enough experiences. So that's kind of what's been happening with the fast reactor R&D in Japan. We kind of did the trial and error, and some of the projects that didn't work, such as Monju decided to shut down, and but we still go on the fast reactor development according to the strategic roadmap. So in order for us to balance between safety and innovation, I think that we need to have the right attitude towards safety, and Well, and I think, especially in Japan, that's very important for us to proceed with the fast reactor and other types of reactor development.
Thank you very much, Nakatani-san. I'm afraid that we are out of time. We have reached the end of our allotted period for this discussion. I do want to thank all of the speakers, all of the panelists, not only for their outstanding presentations, but for these very thoughtful reflections on some very, very important issues for the future of nuclear energy and the outlook for nuclear energy innovation. I must say I come away from this discussion feeling quite optimistic based on the comments that we've had and the reflections from the panel. And it remains for me to say thank you to all of the panelists, and thank you to the ICEF2020 organizers for making this truly global discussion possible. Thank you very much.